So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, is welcoming you all to a new amazing video in which we're gonna be working on the Gaussian expression for the gamma function, right? Basically, the Gaussian is let me just show you that Gaussian expression of gamma function. And I would say this is extremely important to understand, right? And this is really important in gamma function. Gamma function. So basically it is gamma of z equals limit n tends to infinity of n to the z times n factorial over z times z plus 1 all the way up to z times z plus n. So this is what we are going to prove in this video. Actually, you know what, these things are not like falling under the category of basics of gamma function, although we have talked about the introductory part of gamma function and I have a video of that as well, right? But this type of things like Weierstrass product, I have proved this, right, of gamma function, and this is gamma of, it's the reciprocal of gamma function. So it is basically z times e to the Euler-Mascaron times z and times the infinite product as n goes from 1 to infinity of 1 plus z over n times e to the negative z over n. So this is what the Weierstrass infinite product, right? There are several ways by which we can prove this down. Even I did that using the Euler-Mascaron definitions and some we did that, right? So, and I would request you to watch that video. And we have some Euler expression as well, which we are gonna prove. Like, I haven't proved the Euler's expression yet about the for the gamma function. So basically it is gamma of z equals 1 over z times the product as n goes from 1 to infinity of 1 plus 1 over n whole to the z and times n over n plus z. So this is the Euler's expression of the gamma function, right? Although I haven't proved that yet, but using this thing actually, I was about to, like, you know what, basically I was solving something, right? So I need to use this equation. I need to use this Euler's expression right over there. So for that case, like if you want to just make a video on that, so I need to use this, but I haven't proved this yet. So I think let's just prove this down in front of you all, and then I'll be proposing that video, right? And for this one, I have to work on this one, right? So it's gonna be the second video, the proof of this one using this Gaussian expression, right? So now let's talk about the Gaussian expression first here, right? Okay. So, you know, the basics of gamma function. Again, I would request you to watch the introductory video of the gamma function. Let's just release this. And I'll just paste the link of that video in the description box of this video. Don't worry about that. So we know that z, or let's say gamma of z equals z minus 1 factorial, right? Okay. So z minus 1 factorial can be written as z minus 1 factorial can be written as z factorial over z. Pause a bit here. Like z factorial means z times z minus 1 times z minus 2 times all the way up to 3 times 2 times 1, right? So basically, if we got rid of the first z over z, because we are having z in the denominator as well, so we would be having z minus 1 times z minus 2 and dot 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 all the way up to 3 times 2 times 1. So basically that is z minus 1 factorial. So hence we can write this as, it's not extraordinary stuff. And now let's introduce something. So we can write this as 1 times 2 times 3 and all the way up to z, right? And I'm introducing something, z plus 1, z plus 2, all the way up to z plus n over, because I have multiplied this extra terms here, like these extra terms, z plus 1 times z plus 2 and times all the way up to z plus n. So I have to divide it with all those stuffs because eventually we have to get that, right? So we are having z here and we have to divide this, like we have to just write all the stuffs here, right? So it's z plus 1 times z plus 2 and all the way up to z plus n, because eventually we got rid of this z plus 1, z plus 2 and that one as well. So we would be having z times z minus 1 times all the way up to 3 times 2 times 1, which is z factorial, and over z. So I hope you are not getting overwhelmed about that. It's not overwhelming part, guys. Please wait for that moment when something big is coming actually, and that is why Carl Friedrich Gauss was known as the prince of mathematicians. He was extraordinary. He was extraordinary, right? Okay, now let's just come back to this. Okay, so we are having something sort of there, right? Now what? Okay, now we can do something there. Wait a second, let me just. Okay, now let's talk about this. This is just crazy. This is being crazy part. So this is gonna blow your mind. We are having, let's talk about the numerator first. So we are having numerator as 1 times 2, which is actually z factorial if you can relate it with that. So z factorial and times z plus 1 times z plus 2. Basically it is z plus n factorial, because z plus n times z plus n minus 1 times dot all the way up to z plus 2 times z plus 1 and times z, and again we are just getting up to, like, multiply up to 3 times 2 times 1. So basically it's z plus 1 factorial, I'm sorry, z plus n factorial. So it's z plus n factorial. And you know what, there are several ways by which we can write this. The first one is written over there. So it's 1 times 2 times 3 times z plus 1 all the way up to z plus n. That's pretty good. And now if we talk about, well, just take a look at there. Let's talk about n plus z factorial, although they both are same, but I've just changed the order. And now I'm not gonna consider z, I'm just gonna consider n, right? It means z is getting vanished, like this, in this equation n is getting vanished, because here from n z plus n and then n minus 1, and here I can write this as z minus 1, and yeah, we can write this as, so basically it's 1 times 2 times 3 times all the way up to n times n plus 1 and all the way up to it's n plus z minus 1 and n plus z. They both are same, and I hope that you guys are not getting confused about that, because basically we are just expanding these two expressions in such a manner that we are getting both of these things actually. Well, we can write, because if we replace z with n and n with z, so that's gonna be like, yeah, I hope you guys are getting that. It's not difficult. Yeah. Well, if we can write, if we are just vanishing n here, so why we cannot vanish z? We can vanish that, because eventually we want to solve for z plus n or n plus z factorial. So yeah, so this is what we are going to work on from now. So basically the numerator is gonna be, so we are having z minus 1 factorial equals, but let's just write this down. So it's 1 times 2 times 3 all the way up to n times n plus 1, and this is all the way up to n plus z over, and we are having denominator as z times z plus 1 and dot 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 all the way up to z plus n. Okay, so we are having that much amount of thing, and now we can write this product like this one. We can write that as n factorial. So that's gonna be z minus 1 factorial equals n factorial, right? And we are having n plus 1 times n plus 2 all the way up to n plus z over, we are having z times z plus 1 times z plus 2 all the way up to z plus n. Yeah, that's amazing, right? Okay, now you know what I'm gonna do here. I'm just gonna, well, I'm not doing this. Gauss did that. So he did, let's just multiply with n's z times. Like, basically what I'm saying is you have to multiply n z times, right? So basically n times n times n times n up to z times. So basically that's gonna be n to the z, right? So why I'm doing that, just wait for the Gaussian magic. Okay, so basically we are having n to the z times n factorial in the numerator, right? And we are having, well, I'm just gonna write this n to the z as n plus 1 over n, right? Like, I'm just gonna take one n out of n to the z in the denominator of this term, and so for the next term, and all the way up to n plus z over n, because from 1 to z, so it's gonna be n to the z, right? So don't get confused about that. And we are having in the denominator z times z plus 1, z plus 2, all the way up to z plus n. Okay, now the crazy part is coming here actually, and you know what? This is easy to prove. You just have to take care about this crazy part, and then you just have to you have to just take care about this part actually. And you know why? You know what? Actually, why I did that? Actually, Gauss did that. Basically, we know that limit. Let's talk about the limits now. So we know, right? Actually, let me just prove this to you. It's not difficult. Limit of n tends to infinity of n plus 1 over n, right? We can write this as limit n tends to infinity 1 plus 1 over n. And when limit n tends to infinity of 1 over n, it's 1. Basically, it's 0, right? 1 over infinity, we consider it as 0, like tending to 0. So basically this is going to be 0, and this here we are having 1, right? And like, yeah, any term like limit n tends to infinity of n plus 2 over n. Let's talk about this. So limit n tends to infinity of 1 plus 2 over n. So again, the result isn't gonna change here, because 2 over n, 2 over infinity, or anything over infinity, we just consider it that it is tending to 1. Or basically it is tending to 0. So this part is 0, and we just got this 1 here. And now, basically why I did that, we are gonna take a limit n tends to infinity here. And that's when we got rid of these all terms, because they all gonna be 1, right? And then, actually this is correct, right? But in order to just get rid of all these products, we actually Gauss did that. But it's alright. If you don't want to play around limits, so that's your final expression, right? But let's introduce the limits as well here. So we are having z minus 1 factorial equals limit n tends to infinity. So as I explained you, like each term is gonna be 1. This is 1, this is 1, this is also 1. So we would be having n to the z times n factorial over this, the denominator, z times z plus 1, z plus 2, all the way up to z plus n. And here is your final result. Basically, z minus 1 factorial is gamma of z. So hence gamma of z equals limit n tends to infinity of n to the z times n factorial over z times z plus 1 times z plus 2 all the way up to z plus n. And here is your final result. Like literally, it wasn't that difficult to prove, I would say. Actually, my electricity has gone, that's why I'm quite getting sweat here, but it's alright. Yeah. So, it wasn't that difficult to prove. And you know what? Believe me, the Euler's expression is literally a piece of cake when we talk about this one. When we have proven this one. So, yeah, I would request you to just come up over that video as well, and you would just feel what is gamma function actually. Yeah. So again, guys, if you got to learn something from this video, just make sure to like, subscribe, and share. And if you have any kind of doubts so far, you're free to ask me in the comment section. I'll be there for your questions. And now I would just request you to just come up for the Euler's expression, right? Actually, you know what? When I'm gonna record this video again for the Euler's expression, when the electricity would be right here, I would be just recording that. Yeah, it's quite personal, but it's alright, guys. I don't mean that you guys are different from me. Goodbye, guys. Take care. Love you and be careful. Love mathematics. Love yourself as well. Goodbye.